Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime Series 26, Episode 7, for broadcast on the 16th of January 2023. Coming up on SpaceTime, a strange signal coming from the galactic center, water-rich fractured halos discovered in Gale Crater, and the spectacular green comet on its way to Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A mysterious excess of gamma rays radiating out from the Milky Way's galactic bulge, which astronomers have long thought could be a potential signature of dark matter, may actually be a vast population of millisecond pulsars. The findings, reported in the journal Nature Astronomy, are based on new computer models which provide an alternative explanation for this galactic center excess. The galactic center excess is an unexpected concentration of gamma rays emerging from the center of the Milky Way galaxy that's long puzzled astronomers. Gamma rays are the form of electromagnetic radiation with the shortest wavelength and highest energy. One of the study's authors, Associate Professor Roland Croker from the Australian National University, says this particular gamma ray signal, known as the galactic center excess, could be coming from a specific type of rapidly spinning neutron star. Neutron stars are the superdense stellar cores of stars between 8 and 20 times the mass of our Sun, which have exploded as core collapse supernovae at the end of their lives. These blasts are so powerful they can briefly outshine an entire galaxy. And as the supernova explodes, it crushes down on itself, all the star's gravity falling inwards towards the center, with so much pressure and energy it forces the negatively charged electrons and positively charged protons in the core of the star to squeeze together, forming neutrons, hence the star's name. And under the right conditions, these can spin up, increasing their rotation, becoming millisecond pulsars, rapidly spinning neutron stars, which are rotating at over 100 revolutions per second, like bright beacons shining in the night. However, it gets a lot more complicated than that, because the author's calculations suggest that there simply couldn't be enough neutron stars in the galactic bulge to generate the sort of levels of gamma ray excess that have been observed. So, to provide the additional input, a process known as accretion-induced collapse was introduced. Now, this causes very massive white dwarfs, known as oxygen-neon white dwarfs, to transform into millisecond pulsars. White dwarf stars are the dead stellar cores of smaller stars, like our Sun. When stars like our Sun reach the end of their lives on the main sequence and cease fusing hydrogen into helium in their cores, the balancing act between the outward push of fusion energy and the downward push of gravity ends and gravity wins, and consequently the core starts to collapse in on itself. However, it soon reaches a limit where temperatures and pressures get high enough for a new type of fusion to take place. The helium fuses together to form oxygen and carbon. At the same time, because the core is smaller and thus further away from the surface of the star, the surface becomes cooler, turning more reddish in colour. Being further away from the core, the outer surface of the star is less gravitationally bound, so it expands outwards. The star has become a red giant. Eventually, the helium fusion in the star's core also reaches an end. And for a star like our Sun, there's not enough mass there to allow the star to convert the oxygen and carbon into heavier elements. Without enough gravitational mass to generate the pressures and temperatures to achieve this, the nuclear fusion process comes to an end and the star dies. Eventually, the star's outer gaseous envelope will separate and float away as a planetary nebula, leaving behind the now exposed white-hot stellar core. A white dwarf, which will slowly cool over the eons. and this will be the fate of our sun in about 7 billion years from now. But if a really massive white dwarf, maybe 6 times the mass of the sun, is in a binary system with another star, it can draw material off that stellar companion. And if it builds up enough mass, it can suddenly implode in what's called an accretion-induced collapse event, forming a very rapidly rotating neutron star, a millisecond pulsar. Croker says the new findings don't throw any doubt on the existence of the gamma-ray excess signal, but it simply offers millisecond pulsars as another explanation for the potential source. Now, astronomers have previously detected gamma-ray emissions coming from individual millisecond pulsars in the neighbourhood of the solar system, so we know that these objects do emit gamma rays. What the new work seems to demonstrate is that the integrated emission of a whole population of these stars, around 100,000 in number, would produce a signal entirely compatible with what we see in the galactic centre excess. Now, if this discovery turns out correct, scientists will need to rethink exactly where to look for new clues to try and explain dark matter. Dark matter is a mysterious invisible substance. Scientists know it exists because they can see its impact on galaxies, preventing them flinging apart as they rotate. And they know there's a lot of it there. Calculations suggest it makes up more than 80% of the total mass of the universe. In other words, less than 20% of the universe as we know it is made up of stars and planets and people and dogs and cats, houses, cars, and everything else we think of. And if you're a scientist, understanding that you know so little about the universe comes as a rather uncomfortable realization. Croker admits the very nature of dark matter is entirely unknown, so any potential clues garner a lot of excitement. But he says that these new results are pointing to another important source of gamma-ray production. And the Milky Way isn't alone. For instance, the gamma-ray signal from Andromeda, the next closest really large galaxy to our own, may also be mostly due to millisecond pulsars.
This signal, which is called the galactic centre excess, was discovered about a decade ago, and it was discovered in data provided by an orbiting instrument, something called the Fermi telescope. And the Fermi telescope is an instrument that operates in the gamma ray waveband. So it detects very, very high energy photons, so particles of light which have energies about 1 billion times more energetic than optical light that we can detect with our eyes. The instrument, which is run by NASA, scans the entire sky and basically makes an updated picture of the universe as seen in gamma rays from the Earth. We have to be above the atmosphere to detect gamma rays because they don't penetrate through our atmosphere.
Thankfully.
Yes, that's right. It was realized by some people very early after the launch of this Fermi instrument that essentially there was a signal which was coming from the central regions of the galaxy which they couldn't explain. The signal actually looked like a very good candidate to be explained by dark matter, and a particular type of dark matter called a weakly interacting massive particle. So the idea is that we know that actually most of the matter of the universe is composed of this stuff called dark matter, but that's just a name. We actually, as scientists, don't know what dark matter is. There are various theoretical ideas, and one of the best motivated theoretical ideas for the past, say, 30 or 40 years has been that the dark matter is a type of particle called a WIMP, which means a weakly interacting massive particle. And the same sort of theoretical ideas suggested that the WIMP dark matter candidate might be able to undergo a process called self-annihilation. So that means that if two WIMPs collide with each other, they can actually annihilate. And from that annihilation, you get a spray of daughter particles, including gamma rays. We know that the dark matter density in the galaxy should reach its largest values towards the center of the galaxy. So if you wanted to look for a signal from dark matter self-annihilation from these hypothesized WIMPs, then what you might do is point your gamma ray telescope towards the center of the galaxy and look for a signal. And so the discovery of this galactic center excess signal in the Fermi data was a sort of a walks like a duck, quacks like a duck sort of argument. The signal was in the position where you might expect the dark matter signal to come from, and then there were some other details about the signal which actually made it look like a very good candidate to be supplied by these WIMP annihilations. So not only does it come from the center of the galaxy where you'd expect it to come from, but it dies off in a characteristic way with distance away from the centre of the galaxy. So it has a sort of a radial dependence. So it reaches a peak intensity when you're pointing right at the galactic centre, and then as you increase to the angular separation from the galactic centre, it dies off in intensity.
Is this basically along the disk of the galaxy you're talking about, or in all directions?
In all directions. So,
all right.
So initially the signal looked like it was basically circular, radially symmetric. So it's a circular signal, and that was one of the things that made it look like a dark matter signal and not something else. And finally, the signal has a particular spectral shape. So that means that if you plot the flux of gamma rays which you detect versus the energy of the gamma rays, then that curve has a certain shape, and it appears like a bump. So most of the gamma rays from this signal are coming out at a particular gamma ray energy of around 2 giga electron volts, so about 2 billion times more energetic than photons of light that we can detect with our eye.
Now, this is very different, I take it, from the Fermi bubbles.
Well, yes. So it's from a region of the sky which has some overlap with the Fermi bubbles. But the signal is more or less circular, and it extends maybe 20 or 30 degrees away from the galactic center in all directions. And the Fermi bubbles don't look like that. They're noticeably, they're very non-circular, and they extend to larger angular scales, more like 50 or 60 degrees away from the galactic center.
Above and below the center, yeah.
That's right, above and below the centre. There's some question about exactly how this galactic centre excess sort of blends into the Fermi bubbles. Anyway, so this galactic centre excess signal was noticed very soon after the Fermi telescope was launched by some external people working with the Fermi data, people like Dan Hooper and colleagues of his. And there was initially quite a lot of resistance to that discovery, but then subsequently many other people have done the analysis and found basically the same signal. And so now the existence of the signal is well established, including by the Fermi collaboration, which runs the Fermi telescope itself. So everybody basically agrees that the signal is there, but then that's separate from the question of what the signal actually represents. It was also, noted pretty early on too, once Dan Hooper and other people had announced the discovery, that there were aspects of the signal which looked like the sort of gamma ray signal which we detect from a particular sort of astrophysical source, and that's something called a millisecond pulsar. A millisecond pulsar is a neutron star which has a magnetic field and which rotates very quickly, about hundreds of times a second. And there are individual millisecond pulsars, which are relatively close to the solar system, which the Fermi instrument detects as individual gamma ray sources. And the sort of spectrum that these things produce looks quite similar to the galactic center excess. So the galactic center excess is not a point source on the sky. It's an extended, apparently diffuse region of gamma ray emission. But the idea here is that what you're seeing is the effect of a large population of these millisecond pulsars.
Now there are a large population of neutron stars towards the galactic center.
Right, that's right. So we have theoretical expectations about what sort of populations of these objects there might be in regions of the galaxy. So an important development that's happened in the last couple of years is that, as I was saying before, it looked initially like the signal, the galactic center excess signal, was basically circular, and that meshed with the idea that it was dark matter. That's the expected shape that you would have, basically a featureless sort of circle. In the case of the signal, really is due to dark matter. But more detailed investigation of the Fermi data suggested instead that it was not actually circular, but it in fact traced the distribution of the stars in the inner part of the galaxy. And these stars are in a structure called the galactic bulge. And the galactic bulge, which we see from the position of the Earth, is not exactly circular on the sky. And when you do a detailed analysis, the sort of asymmetries that the bulge exhibits, they're mirrored by the galactic center excess signal. So in other words, it looks like from this argument, it looks like, again, there's an astrophysical source which is supplying the gamma rays rather than...
Sounds like the duck's back.
Yeah, right. So that was a problem for the dark matter idea. So this further motivates the idea that one should look for an astrophysical source as the origin of the galactic center excess. So that's what we did in our paper with a theoretical model. And what the model did was it basically predicted the population of millisecond pulsars that should belong to this bulge region of the galaxy. And once we had that prediction for the population of millisecond pulsars that would be in that region of the galaxy, we could then predict what the sort of aggregate emission of gamma rays from that population would be. And that prediction is a very, very good match to the actual observed signal, both in terms of its overall intensity, the strength of the signal, and also the spectrum of the signal, the shape of the signal when you plot the flux versus the energy of the gamma rays. We're looking at a particular scenario here for the origin of these millisecond pulsars. So people have mostly had the idea in the context of the galactic center that the millisecond pulsars would come from something called recycling. And with that idea in mind, they could say, well, actually, it can't be recycling for the reason I'll now explain. In the recycling channel for producing millisecond pulsars, what happens is you have a binary system, so two stars that are orbiting each other. At least one of the stars is very massive. It's 8 times the mass of the sun or more. And that undergoes something called a core collapse supernova. And the result of that core collapse supernova is that star basically turns into a neutron star. And then the binary can continue to evolve, and subsequently, and it can happen when the system is very, very old, many billions of years old, that the secondary, the companion of the neutron star, can grow into a giant star, and the neutron star then starts to strip mass off this binary companion. So it accretes matter from the standard envelope of this big red giant, or whatever the secondary has become. And as it accretes that matter, the neutron star, which is kind of old and rather inert, starts to spin quicker and quicker. And this is what is called recycling. And as it spins quicker and quicker, it then becomes active as a gamma ray emitting millisecond pulsar. All right, so that's a sort of generic recycling scenario. But the problem with a recycling scenario for the millisecond pulsar population you would need to explain the galactic center excess gamma ray signal is that in this recycling process, as the neutron star accretes matter from its binary companion, it essentially appears as something called a low-mass X-ray binary system. So in the accretion process, the accreted gas, which is falling onto the neutron star, becomes extremely hot and it radiates in X-rays. And from looking at some stellar systems where we can see both millisecond pulsars and these low-mass X-ray binaries, we can develop an expectation for how many of these low-mass X-ray binaries there should be corresponding to a given level of gamma ray emission. So essentially, the recycling scenario predicts that the part of the galaxy should be filled with these low-mass X-ray binary systems. And we simply don't see those low-mass X-ray binaries in the center of the galaxy. We see many fewer than we would with the idea that it's recycling that's explaining the origin of the galactic center excess signal. So that seems to rule out the idea that millisecond pulsars are the origin of the signal. But that whole idea doesn't consider that there's another channel for the production of millisecond pulsars, and that's what we looked at in our paper. And this other channel is a bit more complicated, but the main thing is that it doesn't produce nearly such a large population of low-mass X-ray binary systems. In this other channel, which is called accretion-induced collapse, what happens is that the primary star, you still need a binary system, and you still need to have, it still has to be a relatively close binary system so that you can have mass exchanged between the stars in the binary. But the primary star is somewhat less massive than the star that you have in the recycling scenario. In the recycling scenario, the primary star is more than 8 solar masses, and it undergoes a core collapse. In this accretion-induced collapse scenario, that primary star is probably between about 6 and 8 times more massive than the sun. So it's not big enough to undergo a core collapse supernova. Instead, its main sequence life ends when it becomes a very massive type of white dwarf, a particular type of white dwarf called an oxygen neon white dwarf. The important thing about these white dwarfs is they're very massive, and they're just below this famous Chandrasekhar mass limit of 1.4 times the mass of the sun. In the binary system, if there's accretion again from the secondary onto the primary, this white dwarf system, the importance of the accretion is not so much that it spins up the white dwarf, but as the white dwarf approaches this 1.4 solar mass Chandrasekhar mass limit, it undergoes something called an accretion-induced collapse. So basically, there's a nuclear process called electron capture, which happens in the core of the white dwarf, and the white dwarf basically collapses very suddenly down into a neutron star. This is an implosion rather than an explosion, as in a supernova. And then you get an effect, as the white dwarf is many thousands of kilometers in radius, and and then it collapses down into a neutron star, which is something like 10 kilometres in radius. And so you get an effect like what happens when an ice skater brings their arms in as they're pirouetting. So they start to spin much more rapidly. And this is exactly what happens with these accretion-induced collapse events. The neutron star, which results from the collapse, is very, very rapidly rotating. So basically, you're immediately producing a millisecond pulsar, so a neutron star which is rotating, hundreds of times a second. And so we traced the evolution of this population in a numerical model, which looks at the evolution of the stars in this bulge region of the Milky Way. So these are stars which are mostly very, very old, actually. They're mostly formed something like 10 billion years ago. But the binaries with certain characteristics, the ones that are sufficiently close and with stars in the correct initial range of masses, they go on to form this population of millisecond pulsars from this accretion-induced collapse process. And what we showed is that, as I said before, that we get a population of millisecond pulsars, and the gamma ray emission from that population we can calculate, and it's a very, very good match to the galactic center excess gamma ray signal. But at the same time, and importantly, we don't predict a population of these low mass X-ray binary sources, which is more than we see from that region of the galaxy. So you can basically produce the gamma rays without producing too many X-ray point sources.
That's Associate Professor Roland Croker from the Australian National University. And this is SpaceTime. Still to come, water-rich fractured halos discovered in Gale Crater, and the green comet on its way to a flyby of the Earth. All that and more still to come on SpaceTime. Scientists have discovered fracture halos containing water-rich opal on the floor of Gale Crater on the red planet Mars. The findings, reported in the Journal of Geophysical Research Planets, are based on an analysis of readings from NASA's Mars Curiosity rover and its Neutron Spectrometer Dynamic Albedo of Neutrons, or DAN instrument. In 2012, NASA sent the Curiosity rover to Mars to explore Gale Crater, a large impact basin with a massive layered peak known as Mount Sharp in the middle. As the six-wheeled car-sized rover worked its way across the Martian surface, scientists noticed these light-coloured rocks surrounding fractures which crisscross the vast landscape, extending out as far as the horizon. Recent studies by Curiosity have shown that these fractured halos, as they're called, contain opal. Now, the discovery of opal is noteworthy because it can form in scenarios where silica is in solution with water, a similar process to dissolving sugar or salt in water. And if there's too much salt or conditions change, it can begin to settle at the bottom. Now, here on Earth, silica falls out of solution in places like lake and ocean bottoms, and it can form in hot springs and geysers, environments similar to that found at Yellowstone National Park. When we think of opals, we think of the beautiful rainbow-coloured gemstones. But it's predominantly made up of just two components, silica and water, with minor amounts of impurities such as iron. Now, as opal isn't actually a mineral, the water in it isn't bound as tightly as within, say, a crystal structure. This means that if you grind an opal down and apply some heat, the opal releases its water. And when you think about it, that makes opal a potential water source for future astronauts exploring the red planet. Now, following the recent confirmation of opal in these fractured halos, scientists went back through Curiosity archival data, and they discovered that the rover had driven right over one of these fractured halos many years ago, early in the mission, and a long way from the recent sample. And what the scientists noticed is that these earlier fractured halos not only looked like the halos found more recently in the mission, but in completely different rock units, but it turns out they were also very similar in their composition, comprising a lot of silica and water. Although the study's lead author, Trevor Gabriel from the Arizona State University, wasn't able to perform an exhaustive assessment of water content in all the halos observed, he and his colleagues were able to undertake a dedicated neutron experiment on two of these halos, finding that just a single metre of halo could house roughly 3.8 to 5.7 litres of water in the top 30 centimetres of the Martian soil. The poles on Mars house lots of water ice, as well as other volatiles like carbon dioxide. And even in the upper latitudes, we know there's lots of permafrost just beneath the surface. But in present-day Mars, water is very rare at the equator, with absolutely no widespread evidence of water resources anywhere near the surface. What this study therefore suggests is that water-rich opal may be lining landscapes across regions of Mars where scientists otherwise wouldn't expect to find water. And surprisingly, the opal in Gale crater retains water despite the dry conditions of the modern-day atmosphere. Gabriel says these fractures seem to extend right across the crater floor. And that suggests not only that there could be vast subsurface fracture networks providing lots of water, but if these subsurface fractured networks are hollowed out, they could also provide shielding for astronauts from the red planet's inhospitable surface conditions. In Gale crater, for example, temperatures can easily go below minus 74 degrees Celsius on a cold winter's night. And even on a warm afternoon in Gale crater, temperatures barely go above 1 degree Celsius. And of course, Gale crater, and really anywhere on Mars, also experiences far more radiation than the surface of the Earth due to the thin Martian atmosphere and lack of a planetary-wide magnetic field. For astronauts, what that means is that every day spent at a place like, say, Gale crater would expose them to a cosmic source radiation dose as high as a daily chest or pelvic X-ray. Not the sort of thing you want to endure on, say, a 6-month mission to the surface of the red planet. This SpaceTime. Still to come. Skywatchers around the world are in for a treat, with a once-in-50,000-year comet making a rare appearance in the next few weeks. And later in the Science Report, Australia to buy new American and Norwegian rocket and missile systems. All that and more still to come on SpaceTime. Skywatchers around the world are in for a treat, with a once-in-50,000-year comet making a rare appearance over the next few weeks. The celestial visitor, named C2022E07, was discovered last March as it passed Jupiter by astronomers with the California Institute of Technology's Wide-Field Survey camera at the Zwicky Transient Facility. C2022E07 is what's known as a long-period comet, which spends most of its time well over 2,500 times further away from the Sun than the Earth. In fact, it's visiting the inner solar system all the way from the Oort cloud, a vast hypothetical sphere of comets, icy worlds and frozen debris far beyond the planets, which are being caught in the Sun's gravitational pull and are now travelling with the solar system on its journey around the galaxy. Some of these objects may have been formed 4.6 billion years ago when the Sun and protoplanetary disk were formed, while others could be hitchhikers from other star systems. Right now, the 1 kilometre wide comet is making its closest approach to the Sun, but it won't be visible in Australia until it makes its closest approach to Earth on February the 2nd, at which time it will still be some 42.5 million kilometres away. But for our listeners in the Northern Hemisphere, the comet's already become visible, and it's easy to spot with a good pair of binoculars or backyard telescope. C2022E07 is estimated to be shining with a magnitude of around 11. Magnitude describes the brightness of an object, with the higher the number meaning the darker it is, and the lower the number meaning the brighter the object is. The comet will be at its brightest when it's closer to the Earth, and it could even be visible as a naked eye object in dark skies away from city lights or a bright moon. So because of the full moon in early February, the last week of January will be a good time to try and spot it. Just look between the constellations of Ursa Minor and Ursa Major. Another opportunity will be around February the 10th, when it passes close to Mars. Just look for the fuzzy green dot next to the solid red dot. I say fuzzy green dot because it has a bright green aura around it, an envelope of dust and gas formed around the nucleus due to the evaporation of surface ices and internal volatiles due to the heat of the Sun. Among those closely watching the comet will be astronomers, including those from NASA's James Webb Space Telescope. They'll be studying the comet's composition and chemical makeup. See, the closer the comet is to Earth, the easier it will be for telescopes to make detailed observations of the comet and how the Sun's heat has boiled off its outer layers. And a long-period comet like C2022E3 being such a rare visitor to the inner solar system, provides astronomers with a lot of information about the sorts of objects that are hanging out in the Oort cloud. And it's not like we get a chance to do this a lot. The last time C2022E3 passed Earth was during the Upper Paleolithic period, when Neanderthals roamed Europe and Central Asia. And as for its return visit in another 50,000 years, well, right now we're not sure that's even going to happen. See, there's a strong possibility that as it swings round the Sun, the orbit of this comet will change. And so instead of simply returning to the Oort cloud and then coming back into the inner solar system, it will be flung out of our solar system altogether, joining a vast population of interstellar objects, inhabiting the spaces between the stars. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study of Californian prison inmates has found that the recent COVID-19 vaccination and booster program has reduced the infectiousness of the first Omicron wave, but the overall infection risk remains high. The findings, reported in the journal Nature, confirm that vaccination and boosting, especially when recent, help to limit the spread of the virus between people living in the same cell. The study's authors analysed data collected by the California Department of Corrections for 111,687 inmate residents, 97% of whom were male, between December 15, 2021 and May 20, 2022. Still, breakthrough infections were common despite the relatively high vaccination rate of 81%. But the rate of serious illness was low. In just over 5 months, there were 22,334 confirmed SARS-CoV-2 Omicron infections, 31 hospitalizations, but no COVID-19 deaths. And vaccinated inmates with breakthrough infections were significantly less likely to transmit them, 28% versus 36% for those who were unvaccinated. But the likelihood of transmission grew by 6% for every 5 weeks that passed since the inmate's last vaccination shot. Natural immunity from a prior infection also had a positive protective effect, with the risk of transmitting the virus at 23% for someone with a reinfection compared to 33% for someone who had never before been infected. Over 6.7 million people have now been killed by the COVID-19 coronavirus since it was first detected around China's Wuhan Institute of Virology around September 2019. The World Health Organization now estimates the true death toll is likely to be around 16 million, with over 670 million confirmed cases globally. A new analysis of long-term climate data has given scientists a better understanding of how climate change causes seawater temperatures on one side of the Indian Ocean to become much warmer or cooler than on the other side. This dipole phenomenon can trigger deadly weather-related events like mega-droughts in eastern Africa and severe flooding in Indonesia. The dipoles created by interaction between a heat transport system in the Atlantic Ocean and an atmospheric loop called the Walker Circulation in the tropical Indian Ocean. Now, the lower part of the atmospheric loop flows east to west across much of the region at lower altitudes near the ocean's surface, and the upper part of the loop flows west to east at much higher altitudes. The new findings, reported in the journal Science Advances, are based on 10,000 years of past climate conditions, reconstructed from different sets of geological records that have been ploughed into a new climate model. What it shows is that around 18,000 to 15,000 years ago, melted fresh water from the massive glacier that once covered much of North America poured out into the North Atlantic Ocean. This caused currents that kept the Atlantic warm to weaken, setting off a chain reaction that ultimately led to the strengthening of an atmospheric loop in the Indian Ocean that keeps warmer water on one side of the basin and cooler water on the other. The authors characterize it as an east-west dipole, where the water on one side of the ocean, the western side, the side which borders the modern-day Eastern African countries of Kenya, Ethiopia and Somalia, to be cooler than the water on the eastern side, which borders Indonesia and Australia. They saw that the warmer water conditions of the dipole brought greater rainfall to the Indonesian side, while the cooler water brought much drier conditions to Eastern Africa. The Australian military had to spend more than $2 billion on new American and Norwegian rocket and missile systems. The Army will purchase 20 new M142 HIMARS long-range mobile rocket launcher systems from the United States. The Lockheed Martin-built system, which has already been used with devastating effect against Russian forces in Ukraine, uses a 6-pod launcher mounted on the back of a truck and can fire a range of different missile designs. The new weapons are expected to begin deployment from 2026. Meanwhile, Canberra's also placed an order for new long-range precision strike missiles to replace its ageing stocks of Harpoon missiles. The Kongsberg anti-ship and land attack naval strike missile will equip the Navy's destroyers and frigates from 2024. The 4-metre-long surface-skimming cruise missile has a range of over 250 kilometres. British Royal Navy's ordered the same missile for its new warships, as have the United States, Poland, Malaysia, Germany, Japan, Romania, Canada, Spain, and of course Norway. In September 2021, Canberra also announced that Australia would begin acquiring Tomahawk cruise missiles for its air warfare destroyers and begin work on developing its own missile manufacturing industry. The idea of people hanging together in a secret club isn't new. In fact, it goes all the way back to Fred Flintstone's Loyal Order of Water Buffaloes. From Freemasons to the Bilderbergs, secret societies are as old as human civilization. But when it comes to conspiracy theories, no secret society could ever compete for infamy with the enlightened ones, the Illuminati. In his book, The Illuminati and the Beginnings of a Global Super-Conspiracy Theory, John Robinson describes the Illuminati conspiracy theory as a reflection of a centuries-old ideological war between the upholders of orthodoxy and those they condemn as heretics. At its heart is the fear of a changing world. A world not just merely slipping away, but being actively pulled away. And the Illuminati theory gives a name to those doing the pulling. Now, the Illuminati were real, originally enfranchised in Bavaria in 1776, with the secret aim of becoming members in book publishing houses in order to get cheaper printing prices to make books more accessible to the masses. You see, the Illuminati's aim was not to control the world, but to educate it, provide books and learning to all, and encourage outlandish and dangerous ideas like basic human rights, providing education for women, holding popular elections for government, and separating the law of the state from the law of religion. Shock horror. But as Tim Mendham from Australian Skeptics explains, once the Illuminati's dastardly plans were discovered, the group were quickly outlawed by the Bavarian monarchy, lasting a total of just 10 years.
In your conspiracy circles of groups that are working to overthrow whatever, the one world government or whatever, every skeptic will tell you that the name Illuminati keeps cropping up. And as soon as someone mentions the Illuminati, you go, yeah, been there, done that. The Illuminati started as a small group, a suggestion from Germany during the Enlightenment period, which is the 1700s or whatever in Europe, that it'd be good to teach people about things, like education might be a good idea. And of course, the Illuminati means illuminated, enlightenment. So basically, Illuminati is just a Latin version of enlightenment, nothing more. And it means learning, teaching people how to read, encouraging libraries, that sort of thing. And that's what the Illuminati was. It didn't last long at all. It was a very short-lived movement. It was very small, short-lived. But in conspiracy circles, it had suddenly become the absolute top conspiratorial organization that's running the world. And it doesn't exist. And it really never did exist in any great way. And when the little bit that was existing, it was very benign, quite reasonable suggestions about why don't we teach people how to read, and why don't we give them books, and that sort of stuff. So it's been totally blown out of proportion, but hey, that's what conspiracies are, and it's become this mythical group, this iconic group of people planning. People believe it's real. So, and it's just basically, Illuminati just means enlightenment. And there is nothing more to it than that, except in conspiracy circles. And it's a very interesting psychological assessment when people keep quoting Illuminati. I've actually been invited to join the Illuminati by people who claim they're Illuminati, but they're not, and I didn't join. So it's an overblown group. Now, there are other groups, as has been suggested, that might be plotting against people. That might be plotting to control the world, whether it's a G20 meeting or some group of sort of industrialists or whatever. Actually, the G20 do actually run the world, but they're always arguing with each other and having their different agendas. That is the trouble with groups that are supposedly running the world. They don't agree. If you see any group, any political party, they're always infighting and they're always leaking information. Now, they always hate each other and they leak information about each other. So if you think any particular group is going to be running the world, they're not going to do it very successfully. So, and the Illuminati never did run the world, never intend to run the world, but people keep saying it did, or it does.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.